Shalom לכולם. Hi everybody, I will be speaking English for those who don't speak Hebrew. So welcome to the first session of the department Colloquium at the Computer Science School of Computer Science at the Hebrew University. My name is Roy Schwartz, and together with Ilan Komagotsky, we will be hosting the Colloquium this year. And today we are very proud to introduce Dr. Ofra Amir, which is an assistant professor at the Faculty of Industrial Engineering and Management at Technion. Her research lies in the intersection between artificial intelligence and human-computer interaction. She did her PhD at Harvard and her BSc and MSc at Ben Gurion. And so before we begin, just a couple of technical words. Those of you who have questions throughout the talk are invited either to unmute and ask them or write them down on chat, and I will read them on occasions. And without further ado, I present Ofra Amir.
Hi, you can hear me? Yeah, okay, thanks. So thanks, Roy, and thanks for inviting me. So today I'll talk about some work we've been doing recently in the area of explainable AI, on how to describe the behavior of computer agents, and in particular reinforcement learning agents to people. And as Roy said, please feel free to stop me if you have any questions in some mode. So in general, we know there's a growing number of autonomous and semi-autonomous agents, and these can be physical agents like self-driving cars or robots, and it could be virtual agents like agents that recommend medical treatment or something like that. And what we want to do in this work is improve people's knowledge and understanding of agents' expected behavior. And why would we want to do that? So one reason might be so they can better understand the capabilities and the limitations of the agents, so they can maybe choose better agents among alternatives or decide how much autonomy they should give to an agent, when they can trust the agent, and so on. So we'd like to help them create a better model of how the agent will behave. And this is not trivial because people in general have a hard time forming mental models of complex systems. So this is not something new. It's true for systems that are less complicated than, say, deep learning based agents and things like that. And often the mental models that people establish on how systems behave are incomplete, inaccurate, and unstable. So we want to help them develop better models. And as I said, in general, this line of work is in the area of explainable AI. So I'll just try to distinguish what we're doing a bit from maybe types of work that some of you might be more familiar with. So perhaps the kind of most common or most currently popular works in explainable AI are in the area of interpretable machine learning, where generally, usually it's a supervised learning setting where you have, say, some classifier and you want to explain its decision-making to a person. So one common approach is, say, the LIME algorithm, which tries to tell people which features were important to a particular decision. So if I have my model and I have a training set, and then I make a prediction and I can show which features contributed most to this prediction. Okay, that's probably the most common use now of the interpretable machine learning. And these approaches typically explain one-shot decisions, and they do not describe the model in general, and also they do not address settings where there is a sequential decision-making policy. So the agent actually acts in the world and affects what happens. It's usually a kind of one-shot, here's, say, a patient, and here's the patient's data, and these are the features that were important. And so we're going to try to look at a sequential decision-making setting. And in these sequential decision-making settings, there's also some recent work in explainable AI, which often tries to help people understand, again, a particular decision. What caused the agent to take a particular decision? Actually, caused is probably a strong word here, but often people use things like saliency maps that show what the agent was paying attention to. Okay, so this is an example where people visualize the attention of an Atari agent. And there are some works in this area that take different approaches. And here the distinction I'm going to make is that rather than trying to explain a particular decision, we're going to try to describe a global policy of the agent, okay? And so that's what we're going to try to do. And the name we chose for it, which might not be ideal, is policy summarization. So kind of the key idea is that I want to describe the behavior of the agent in a range of scenarios. Okay, so a trivial solution might be to just have you watch the agent act. So say that it's a self-driving car, I can just show you a video of the car driving. Okay, but this might not be a very good solution because first, it might take a lot of time. And second, it might not be efficient in the sense that say that the car is stuck in traffic for an hour, you don't really need to watch it being stuck in traffic for an hour. And so what we're going to try to do is choose a set of states where we will demonstrate what the agent does. And we'll talk about how to choose this state, but just as an analogy, imagine that I'm trying to describe my agent is Michael Jordan, and I'm trying to describe the capabilities and limitations of Michael Jordan and how he's playing basketball. So instead of having you watch 80 games in an NBA season, I can show you a sort of highlight summary that will demonstrate some of Michael Jordan's skills. So I can show you Michael Jordan shooting and dunking and maybe passing the ball and maybe defending. Okay, and unlike this video, it doesn't have to be only successful scenarios, okay? It might be also scenarios where the agent is not performing well. Okay, so that's kind of the high level idea. If there are any questions about the general problem, might be a good point. Okay, and so I'll define it formally. We're going to, yes.
Technical problems. Due to technical problems, I joined just now. If you can give a 2-second summary, I will be really grateful.
Sure. And so in general, we have an agent, okay? It could be a reinforcement learning agent. It doesn't have to be, but we're going to assume that there is a Markov decision process that the agent acts on. Okay, so we have a set of states and we have an action. We have the transition function between states. There's some reward function, and the agent has a policy for how to act. And what we're going to try to do is describe to a person the policy of the agent, okay, such that the person will get a sense of how the agent behaves in different regions of the state space. And the way we're going to try to do it is extract what we call a summary, which is basically a subset of demonstrations of the behavior in particular states. So it's actually a good slide to ask this about. And so more formally, what we have as an input, we have the policy of the agent, and we'll assume that we get some budget for how much information we're allowed to show to the user. Okay, so it's like I'm willing to watch, half an hour or 10 states or whatever it is. And we'll have some algorithm, and the output is going to be this summary, which basically contains pairs of states and actions, okay, but only a subset of them. And then the key question is, what should we optimize for when we select this subset? Okay, so we have a large state space, and we want to demonstrate the behavior in a range of scenarios that would give the person a sense of how the agent is acting. And the question is, which set should we choose? Okay, and I'm going to describe 2 approaches we've taken for choosing this subset that optimize for different things. If we'll have time in the end, I'll also show a combination of this approach with local explanations of what the agent is looking at, but we probably won't get there. Okay, so as I said, the main question is what information should appear in this summary? And the first attempt that we've done, and this is a joint work with Dan Amir, who is a master's student at your department, but also my brother. So here we try to choose important or interesting states. And what makes a state important? Our intuition is that a state is important if the choice of an action in that state will have a substantial impact on our expected utility. Okay, so for example, if you're driving in a car and you're on a highway and you reach an exit, and then that might be an important state, because if you miss your exit, it can have long-term implications and it might take you much longer to reach your destination. Whereas if you are, if I'm at the Technion and I try to drive to my faculty, and I miss some turn, it doesn't really matter that much. Okay, and the example here of Michael Jordan is like last seconds of the game making a shot. Okay, so this is the intuition. And our approach is going to be that we're assuming that we have access to the agent's policy and actually also to the Q values, which I'll talk about in a minute. And we have some simulator of the domain. And from now on, I'm going to use Pac-Man as an example, which is the domain we used in our experiments with people. And we're going to try to identify these important states based on the agent's Q values. Okay, and the kind of idea here is that if there is a large gap between the Q values, so the Q value tells me for a combination of a state and action, if I take this action now and then following that act based on my policy, what would be my expected utility? And so if there's no difference between the Q values of different actions, then this decision doesn't really matter, right? Because I'll turn right, I'll turn left, it's all the same. And what we're going to look for is states where there's a large gap between the expected future rewards for the best action in that state and the expected future rewards for the worst action. And this heuristic has been used before in works on how to train agents, when to intervene and give them advice. And we're using it here to kind of look for important states to show a human. So just to give an example, if we're in Pac-Man, so this state is going to be important because a ghost is very close to Pac-Man. So if I turn towards the ghost, I'm going to die and get no future rewards. Whereas if I go left, then I can still accumulate a lot of rewards. Whereas this state on the right is not so important. I mean, there is a difference in the rewards from, say, turning left and eating these pills versus turning right. But if I then later follow my policy, I can still fix it. Okay, so that's the intuition for what makes a state important. Any questions about that? Oi? Oh, I thought you raised your hand, but it's
no.
you just
actually, okay. I do have a small question.
Okay.
So when you talk about, I mean, you mentioned self-driving cars as one of the domains that you were thinking about. And here, when you think about the worst reward, there's always, I mean, jumping off the bridge or something. So how do you take this into account? Or maybe are you defining a smaller subspace of reasonable actions? Or
so yeah, that's a good question. So this heuristic is quite sensitive to this situation where you can always sort of commit suicide or something like that. So one thing we did in later work is take the best and second best action, but you can, I guess more generally, you could look at the distribution of Q values as maybe being more informative. So you're right that this is kind of domain dependent and it worked fairly well in Pac-Man, but it's probably not a good approach in general. Thanks. So we're going to look for states that have high importance score, and as Roy noted, we might want to come up with a better measure, but something about the distribution of Q values can give us a sense of the importance of the decision. And the algorithm that then creates a summary, which we call the highlights algorithm, it takes as input the agent's policy and the Q values and this budget for how many states it's allowed to include, and it outputs a set of state action pairs. And it's a very simple algorithm. We just run simulations online, so you could actually do it during the agent training also. And we choose the states with highest importance. So just to show a quick example, so say that my budget is 5, I'm allowed to include 5 states here in the summary, and I start encountering states and I put them in my summary if I still have room, if I still haven't reached my budget, or if the importance of the state is greater than the importance of the least important state that I have so far. So I start filling out the summary, and now when a new state arrives, so the importance here is 20, and it's greater than 10, so I'm going to push out the state with 10, and so on. Now a state with importance 500 arrives, so I'll push out the less important states, and so on. And so that's the idea. And the only other thing we do is that rather than show single states and actions, it doesn't give enough context. So we show trajectories. We take a window before and after the important state just to give context of where the agent is now. And to show you what this looks like, so this would be kind of the Michael Jordan video equivalent for Pac-Man. And so you can see Pac-Man escaping ghosts and eating pills and so on, okay? And this is extracted based on the Q values. One limitation of this approach is that, and you can see it actually here in the video, you can get a lot of similar states. So the other improvement we've made is also take into consideration the diversity of the states. So if you have some metrics for how similar two states are based on their features, we can also add something that tries to optimize for that. So I will only add new important states if they are also diversifying if my current set, okay? And I won't get into the details, but that's just another optimization goal that we put there. So then we have this set of states or set of trajectories in this case. And the question is now, are these summaries good? Okay, and what does it mean for the summary to be good? So our goal, right, was to help people develop understanding of the capabilities of the agents. So what we did in this evaluation, and later I'll show another type of evaluation, is we did this agent selection task where we show people videos of two agents where we know the ground truth, we know which agent is better at this task. And we ask them to choose which agent they want. In this case, we set it to play on their behalf, and they get a bonus if they choose the agent that actually performs better in practice. Okay, so that's the task. And in terms of the setup, we created 3 different agent levels. So we have kind of a low quality agent, a medium quality agent, and a high quality agent. And we do this simply by training them for a different amount of time. And then the other question is, what do we compare these to? Are these summaries good compared to what? So we have our algorithm, and we also did the baseline, which randomly samples states for the summary. And note that this is not really random because we do it during simulations of the agent's behavior. We have a higher likelihood of picking states that occur more frequently. So this is more like taking frequent states as a baseline, okay? Or choosing states in proportion to how frequent they are. And our third baseline is just taking the first trajectories that the agent encounters. So this is like telling you, start watching the game of Michael Jordan and then turn off the TV when you run out of time, okay? And we had 40 participants online, and it's within subject design, which means that all participants participated in all conditions. So basically they made 9 comparisons. They have, say, the low quality agent versus the medium quality agents with the highlight summary, or the same 2 agents, but with the first trajectories, and so on. And we randomize the ordering. And they, of course, don't know which agents they're seeing. Okay, so this is the design. And what we're going to try to look at is how many times people were correct, okay? So what we can see is that these summaries actually helped. And what we're going to see in the plot here is on the y-axis, we'll have the correctness rate. So if you guessed 9 out of 9 right, you get 1. And on the x-axis, it's separated into the different comparisons of the agents, the low quality versus medium quality, and so on. And this will be interesting because some comparisons are more difficult than others. And highlights div is the highlights diversity. So it's the algorithm that picks important states plus accounts for diversity. Yes.
I have a question.
Yes.
The agent is Michael Jordan, right? Not the viewer.
The agent is, yes, is Pac-Man in this case. But yes, so the way, let me go back to the previous slide. So the agent is Pac-Man, okay? And there are 3 different pacman agents. So this might be the high quality agent, and this might be the medium quality agent. And you'll see the summary will be with the same method. So you'll see, say, highlight summaries for this agent and highlight summaries for this agent. And then you'll see a random summary for this agent and a random summary for this agent. And we're going to try to see which summaries better help people distinguish and identify the agent that's performing better. Does that answer the question?
Yes, thank you.
Okay, great. Okay, so what do we see here? So green is our algorithm, so we're happy. And you see that in all comparisons, we outperform, and this was statistically significant versus the other approaches. Something interesting here is that for the low quality agent versus the high quality agent, which is actually the easiest comparison because the difference in their performance is the greatest, you see that looking at the first trajectories is actually very bad. It's much worse than random, right? If people were just guessing, we'd expect to see 50% correctness rate. And they do much worse when we look at their explanations of why they chose the agent. They said it seemed like the high quality agent was taking more risks. And because they didn't see it succeeding later, they were sort of afraid that it would die from them. So we see that these summaries do seem to help people identify the better agent. And I'm not showing this plot here, but we also asked them, later we showed them the same agent with different summaries, and we asked them which summary they think better describes the agent's behavior. And there too, we see that people subjectively feel that the highlight summaries that look at important states are more helpful. But we were more interested in this subjective measure because in general, people, we also asked them to rank their confidence, and in general, people can be very confident when they're very wrong. So it doesn't seem like they really understand, which also means that it's important in the sense that these summaries can be very misleading. So we need to be careful and maybe also tell people what they're seeing and how these states work. Any questions about this approach or anything I said so far? Okay, so there are several limitations to these approaches. Some of them you already noted, for example, the sensitivity of Q values. And in addition to the point that Roy mentioned about the best versus worst, there's also the issues that the Q values are computed by the agent. And if the agent is not very good, the Q values might also not be very good in telling us whether the state is important. And also it's very heuristic, right? So the second approach, we try to do something that's a bit more principled. And again, I'm going back to what our goal is, right? What do we want people to be able to do from this summary? So if what we want people to do is to really understand the policy of the agent and be able to reconstruct it and predict what the agent will do in new situations, why not just try to directly optimize for that? So the idea in this second approach would be to choose the summary. So on the left, it's a summary, say that I have Michael Jordan. Okay, and I want you to be able to predict what Michael Jordan will do in a state that you haven't seen yet. Okay, and the way we're going to try to do that is looking at approaches for reconstructing policies based on demonstrations, and this relates to the area of learning from demonstration. If people here are familiar with it, and we'll look at 2 approaches. Sorry. One is imitation learning and one is inverse reinforcement learning, and I'll say a bit more about it in a couple of slides. But first I'll describe the kind of general pipeline, and this is a bit more complicated than the previous approach. So again, we're going to have some policy. So imagine that this is a grid world, and every time it's blue, the agent goes right, and the yellow means that the agent goes down. So the policy of the agent here is just go right whenever you're not in the rightmost column. And once you get there, go down. So we're going to have this pipeline which extracts a summary, chooses states for demonstrations, and I'll talk about how in a second. And then it sort of hides the other states, okay? So everything that's in pink here on the right is now unseen, okay? I don't get to see it. The only things I see are these blue, the places that it turned right here, and the yellow actions here. Okay, so we're going to extract some summary. And then from this summary, we're going to try to reconstruct the policy using approaches like imitation learning and inverse reinforcement learning. And then we get a reconstructed policy. It might not be exactly the right policy. It might not entirely accurately reproduce the policy of the original agent. But our goal in this pipeline will be to minimize this difference, okay? We want to make this extracted policy, reconstructed policy, as similar as possible to the original agent's policy. And this is going to be what we're going to try to optimize for when we choose this summary, okay? So we're going to try to find a summary that allows us to recreate and reconstruct the policy. Clear? Not clear? Okay, thanks for the nodding, Ilan. And so one important thing to note here is that this part where we reconstruct the policy, what we would really want to know is how a human would do it, right? Because the summary extraction part, that's what we do. Our algorithm chooses which states to show. But when we show it to a person, the person is going to be the one ultimately doing the reconstruction, right? You see this video I showed you of Pac-Man, and you would try to infer what Pac-Man would do in states that you haven't seen. And one problem is that we don't know what people will do. And so we tried different approaches. And as I said, one was imitation learning, one was inverse reinforcement learning. So just to show an example, say that this is my summary. So I see that the agent turns right in these three places and goes down in this square. So what is inverse reinforcement learning? For those who are not familiar with it, as it sounds, it's the inverse problem of reinforcement learning. So I see what you're doing, and I try to infer your reward function, okay? So, for example, if I'm going to give a talk and it wasn't online, then you would see me going into the classroom and turning on the computer. Then you might infer that I'm trying to give a talk or something. And so in this case, one possible reward function that might explain the behavior that we see with these 4 arrows is having a high reward at the bottom right corner and slightly lower rewards elsewhere. And note that this is problematic in the sense that there are many reward functions that can explain certain behavior and vice versa. There's also many policies that can fit certain reward function. So this is inverse reinforcement learning in one slide. And once we infer the rewards, we can compute a policy, okay, using any MDP algorithm you like, value iteration or whatever. So this is inverse reinforcement learning. Second approach is imitation learning. And here the idea is that I don't try to go through this reward function. I just try to imitate what you're doing. So it becomes a supervised learning problem. It's like developing a classifier from state features to an action. So imagine that my features will be the column in the grid. Okay, so I might say something like, whenever you're in the 3 left columns, you turn right, and whenever you're in the right column, you go down. And I'm not trying to say anything about your reward function. I'm just trying to predict what you will do. Okay. And again, we don't know what people will do. And I should say that also for each of these approaches, there are like hundreds of different algorithms. So it doesn't really stop there. But then going back to our pipeline, this will go here, right, in the policy reconstruction. And then we can choose states. For imitation learning, we can use active learning approaches that try to pick the example that minimizes our prediction, that maximizes our prediction accuracy. And for inverse reinforcement learning, there's approaches that are called machine teaching, where kind of the high-level intuition is that you try to select demonstrations that narrow as much as possible the space of fitting reward functions. Okay, so that's the idea. And I'm not going to get into the details of the specific algorithms. We used existing algorithms here, and we just use them in this pipeline of extracting summaries. And then the question is, does it work? And before we get to does it work, and this time before we did human experiments, we first did computational experiments where we try to ask ourselves two questions. The first one is it important that we match between what we assume in the summary extraction? So when I do the summary extraction, I assume you'll do reconstruction with one imitation learning algorithm or an inverse reinforcement learning and so on. And whether it matters if that matches the actual reconstruction model that you use. And this is important because if it doesn't matter, then that's good news, because then we don't have to know exactly what people will be doing. If it does matter, then it complicates our lives a bit more. And the other question is just whether one approach is better than the other. There is some other work on that, but it seems to be dependent on the domain, basically. Okay, so, and we do this in 3 domains. One is still Pacman, only it's smaller because the inverse reinforcement learning had a hard time. And one is an HIV simulator that simulates the treatment of HIV patients. And the third one is a gridworld with the reward function based on the colors here. And the first thing we see already in the computational simulations is that it does seem important that we know what you're going to use to reconstruct the policy when we're optimizing for the summary. Okay, so if I optimize for imitation learning, but you do inverse reinforcement learning, that's not as good. And what you see here is the prediction accuracy on unseen states. And basically you see that on the diagonal, if I assumed you will be using imitation learning and you did use imitation learning, then I get higher accuracy. Okay, darker is better here than if I assumed you will be using imitation learning, but you actually used inverse reinforcement learning. And also true the other way around. Inverse reinforcement learning works best if you actually use inverse reinforcement learning. So it does seem important, and we see this across the domains. And there are different parameters here for the inverse reinforcement learning and the imitation learning. It doesn't really matter for the purposes of this talk. But in general, we see that it is important to match the two, and that it's not clear in different domains, one of them might be better than the other. So for example, in the grid world, inverse reinforcement learning does best, whereas in the HIV simulator, imitation learning, again, matched with imitation learning, performs best. Okay, so it doesn't seem like one of them will always do better. So then the next stage was to try to do a human subject study. And here, again, we had a few questions. First, how will people interpret the summaries? Will they use imitation learning, inverse reinforcement learning, something else, and so on? Will the summaries help them predict what the agent will do in unseen states? And kind of more generally, will what we saw in the computational simulations even apply to people, or it's gonna just be a total mess, okay? So we ran a study, and we did it in 2 domains. So we used gridworld and the HIV treatment. And this was a 2x2 design, meaning that some people were in a condition where they see gridworld with imitation learning summaries. And again, note that when we create the summary, we're going to assume a matching model. Okay, so this is a summary tailored for imitation learning reconstruction. And some people will see the grid world, but with summaries that were optimized for inverse reinforcement learning, and similarly for HIV domain. And their task is going to be to predict what the agent will do in a state that they haven't seen. So a participant in the experiment might see a summary like this one. So the arrows is where the agent is turning, and there's also a stop action. And then we ask them about some subset of unseen states, what they think the agent will do. Okay, and the better they match the actual policy, the higher their score is. And again, they're rewarded for getting as many actions correctly as possible. And similarly, in the inverse reinforcement learning condition, here the summary includes trajectories because of the way we used maximum entropy for inverse reinforcement learning, and it works with trajectories. So they see really trajectories of actions, but it's the same budget. So they see the same total number of state action pairs, and their task is the same. And similarly for HIV, in HIV, there are the feature space is 6 biomarkers, different tests that the patient does. And they see which treatment the agent chose, and it's 2 drugs, and you can either give only one, only the other one, or the combination of both, or none of them. So there's 4 possible actions here. Okay, any questions about the task or? Okay, so the first thing we saw is that people use different reconstruction approaches in different contexts. So in the grid world, we saw, and how do we know this? We asked them to describe how they generalized from the summary. And so and then we coded it as either being inverse reinforcement learning like, or imitation learning like, or we can't tell. And so here's an example of someone who seemed to think of it in an inverse reinforcement learning way. So he says, I decided that the computer seems to be always working towards the blue square. And then I chose the path to the blue square. So the blue square did have here a high reward. So I'm saying this is inverse reinforcement learning because they try to infer the goal of the agent and based on that, choose a policy. So in this domain, most participants, we couldn't tell what they were doing, but majority of participants that we could tell what they were doing were doing that. Some people were describing something that's more like imitation learning. For example, I tried to compare the colors and choose the action that was most frequent for a color. So say I look at all the arrows in pink squares and I do a majority vote. In contrast, in the HIV domain, we see that almost 80% of the participants did something that seems like imitation learning. So basically they said things like, I chose based on the similarity of blood tests levels from the scenarios on the left, which was the summary. There was only one participant who seemed to be doing something that's inverse reinforcement learning, where they try to infer the effect of the treatment. And we think, we hypothesized that the reason for this difference is that in the grid world, people have some intuition and prior knowledge. They know how you move in the world, so at least the transition function is clear. When you go right, you go right. Whereas in HIV, they don't really know anything. And if you don't know anything, then it's hard to infer something about the reward function, right? You don't even know the transition function. And then just trying to imitate might be a more reasonable thing to do. So the first thing we see is that people might do different things in different contexts. And in general, we see that people are much less accurate than the computational reconstruction. So what you see in these plots, the black dotted line is just random guessing. So there's 4 actions in HIV and 5 actions in grid world. So it's 0.25 or 0.2. And what you see in blue is when we just have our computational pipeline and we extract the summary optimized for inverse reinforcement learning and then actually use inverse reinforcement learning to extrapolate how good do we do, and the same thing for imitation learning, okay? So we see that people do better than random, but much less good than the computational algorithms. And the possible reasons for that, one is bounded computation. So like the example I showed you where a participant said something like, the agent is trying to go to the blue squares, there was actually ordering between the colors. So say blue was the best, but then maybe green and then maybe purple. And people sort of stopped at blue, that was enough for them. And the other thing is that they have various biases and prior assumptions. So for example, in the grid world, we told them explicitly that the decisions are somehow affected by the colors, and that's it. But they would still say things like the agent is trying to get to the middle of the grid and stuff like that. And this also relates to a point that maybe I'll go back at the end to, that I just talked about. We don't know whether people do inverse reinforcement learning or imitation learning. There are many algorithms. And the other thing that we don't know is what the state representation, what state representations the people use. So that's another problem. Okay, so that's the first thing we saw. Regarding whether it's important to match the extraction and reconstruction. So in HIV, we see that participants performed better when they were shown in imitation learning optimized summaries. And if you remember, 80% of participants reported doing something like imitation learning. So it did seem like they benefited from the fact that the summary was optimized for imitation learning. However, in the gridworld domain, we see no difference whatsoever between the summary extraction methods. What we do see is that people, regardless of what summary they were shown, if they used inverse reinforcement learning, so here what I'm showing is not what was used by the algorithm, but what people described in words, right? These people that said, I'm going to the blue squares are the inverse reinforcement learning people, and the imitation learning people are these orange people who try to say, do a majority vote based on the color of the square. And what you see here is what the algorithm assumed. And interestingly, people who gave descriptions that we couldn't understand actually probably didn't understand themselves, right? They're doing like random guessing, basically. But it does seem like here inverse reinforcement learning worked better, which we also saw in the computational simulations, but it didn't matter what summary we showed them, people were able to extract based on that. Okay, so to summarize so far, so we tried to do this kind of more principled approach of optimizing for the ability to reconstruct the summary, but it seems like it's kind of complicated. So in what sense? We saw computationally that it's important to match the summary extraction and reconstruction models, but then in the human experiments, we see that what people might do depends on the context, and beyond not knowing exactly how they're extrapolating, we also don't know their state representation. They also have various biases and so on. So while this approach might sound, as computer scientists, it might sound nicer than the first heuristic because it's sort of, we're directly optimizing for reconstructing the policy. In practice, to do this well, we need a good model of how people actually generalize, and it's not that easy to get. Any questions so far?
Excuse me.
Yes.
Is this supposed to be a psychological talk about psychology? I'm missing something.
This is a talk about human-agent interaction, so about explainable artificial intelligence. And
but essentially, you have to understand people to do that, you're saying.
Yes, I'm saying, and I think a lot
of most of the work is understanding how people think.
I think it's definitely an important part of the work. There's also the algorithmic part, right? We still need to be able to get the policies and to have an algorithm that tries to create explanations. What I'm saying is that I think a lot of, maybe that's a more general claim, that a lot of work in explainable AI and interpretable machine learning is kind of ignoring the people. And I think in this sense, it is important to actually evaluate with people whether these explanation methods are actually helping. And yes, I think that requires understanding of cognitive aspects, psychological aspects, and the design of the approaches. Yeah.
Okay.
Other questions? Okay. So just to recap, so so the idea was to describe the behavior of an agent to people in different scenarios, and then we had two approaches to try to do that. The first used this importance heuristic, and the second try to directly optimize for the reconstruction of the policy. And depending on whether people will have questions, I can talk about some things we're doing now. So one thing we've done recently is try to combine these summaries, so these descriptions of what the agent will do, with saliency maps that show what information the agent is looking at when they're choosing actions. Another thing we're trying to look at, which relates to these approaches that I've discussed, is, and also to the last question maybe, is that maybe the first question we should ask ourselves is, what do we want these summaries to be used for by users? And based on that, choose our optimization method. So for example, one thing we're working on now is if your goal is really to choose between different agents, and this arises, for example, we have collaborators that work on reinforcement learning in healthcare, and you use different algorithms and you get different policies, and you might ask yourself, but how are these policies different? How are they different from a physician's policy, maybe, right? So if that's our goal, then maybe we can directly optimize for showing, say, disagreement between policies, okay? And the last direction that we're starting to think about is having more interactive explanations, which is think about kind of interviewing the agent, right? So this was all kind of, the summary method was black box from the perspective of the human user. We just gave them some summary. But maybe if you're a clinician and you want to test how the algorithm works, maybe you want to ask about specific states or right, or explore in general whether the agent is more risk-taking or what they're optimizing for. And this is particularly important if the reward function is hard to engineer, right? In something like healthcare treatment of chronic conditions, then it might not be clear what exactly, I mean, you want the patient to be better, but maybe you can take a more aggressive treatment that can help more, but is more dangerous, or you can take a more conservative treatment. So that.
תראו סרט, מה שאתם רוצים, אתה צריך להיות פה עכשיו, אלון ישב.
So especially in these domains when the reward function is unclear, it might be important to create explanation methods that help people better understand that. So I can either show a few more slides about the combination of local and global information, or I can just answer questions. So it depends on you.
Yeah, I have a question. First of all, thank you for a very interesting talk. This is very different in the way that I'm used to thinking about these problems. So one thing that struck me as very interesting is that you said that basically, maybe this is how I interpret it, tell me if I'm getting this right, is that when people better understood their decision-making, they were more accurate. I mean, basically when they were better, I mean, they followed what you think was a reasonable strategy and were able to explain it. They did a better job than if they were just, I don't know, implicitly trying to get to the right answer.
So they were doing a better job in predicting what the agent is doing, right? I'm not trying to teach them how to play Pac-Man or something like that. Yeah.
But basically, when they were able to explain to themselves what is it that the agent is doing, rather than implicitly doing it. I mean, in the sense that awareness plays an important role in their success for predicting what the agent does.
So that's a good question. I'm not sure if we actually showed that. I mean, I think what we showed, at least in the first study, was that showing summaries that are based on importance helped people identify which agent is better at the task. In the second experiment, it's harder to say exactly what we showed. We showed that, yeah, it helps people in some sense predict what the agent will do in unseen states, but it wasn't that great. But it's a good question about the engagement. There is some new work from another group that shows that just showing an explanation doesn't necessarily work, but if you force the person first to choose to kind of think about the decision themselves, you do some sort of cognitive nudge to get them to think of what they would do, and then they engage more with the explanation, and that helps them better perform at tasks. So there is some work along these lines too.
Thank you.
Sure.
Can I ask a question, please?
Of course.
Did you consider using decision trees to explain summaries, like rather than just use specific situations, use big decision trees with the number of levels instead of the numbers of summaries incidents?
Yeah, so that's a good question. We haven't tried it, but there is work from another group recently that tried to do that. So they basically try to train a decision tree that would imitate the policy and then show the decision tree. And that can definitely be another approach. The challenges there, I think, are still, which we haven't solved as well, but showing demonstration sort of avoids it, is choosing the state representation. So say that you have a deep Q learning policy, and you want to build a decision tree. So it's a question of what's the feature space you're going to use, and whether people would understand it. So one thing we're interested in is kind of eliciting the state representation that people use when they think about the domain. And then I think it could maybe work better. The other difficulty is that it's sometimes, depending on the domain, hard to get very good accuracy with the decision tree because of the long-term nature of the policy. But it might be useful to do decision trees for maybe different regions of the state space or something like that. So it's definitely a possible approach too.
Thanks a lot.
Sure.
I also have a question.
Yes.
So how do these methods scale? Because when you're looking at how people behave, when you're showing them Pac-Man with these 3 creatures and 1 Pac-Man, I guess it's a little bit maybe possible for humans to see what's going on. But I guess your motivation in the beginning was self-driven cars, where there's like 100 variables around you and not just 2 or 3. And it's not a 2-dimensional problem. It's now much more complicated. So I guess people can't really comprehend so much information. So
so that's also a good question. We haven't looked into that enough yet, I think. That's the short answer, but the longer answer is that so for the second approach I showed, where we need to reconstruct policies, it's even harder because even the computational approach already fails when the state space is large. The importance approach is easy to at least deploy. But I think you're right that if the state space is very large, then one thing that would be interesting to look at is sort of how much coverage you need. So maybe adjusting the budget. We formalize the problem as I have a fixed budget and I try to show you the most important things, but you could think of a different optimization problem of, say, choosing the smallest summary that can help you understand what's going on. And I personally think that a more promising approach will be this interactive explanation approach, where maybe you start with some summary that we generate with an algorithm, but then the person can manipulate the state space. And especially, I think it also depends if the person is an expert user, right? If you think of healthcare, is the user the clinician or the patient, right? They have probably different state space representations and they might care about different things. So I think really the way to address this will be with more interactive approaches that allow the person to explore also freely and not just rely on this automatically generated summary. Any more questions?
Yes, please. Yeah. Did you take into account the probability of states that you chose for the summarization? Because if you take, you talked about Michael Jordan, then you can take highlights, but it won't probably summarize how he acts on the field.
Right. So we did do it to some extent with the random baseline in the first experiment, because it was random from simulations of the agent. So it was really choosing states that are more likely to be encountered. But you're right that it could be added. You might want important states that are also frequent, although in some scenarios, right, you might care about a state that's not frequent if the car is going to explode or something. I think, so first there's a recent work that sort of extended highlights, not from us, and added a lot of different criteria. So one of them was frequency, and others were, they were trying to infer sort of goals and try to look at things like local maxima or local minima, things like that. So you could definitely, I think the framework is quite general, and you could think of different criteria. And I think the other thing is that it will be important to tell people what the criteria were, right? Because if you're showing, like you said, if you're showing a state that's, I don't know, there's only 1% that you'll ever encounter it, it's very different than if you show a state that occurs all the time. So yeah, definitely a good idea. Okay, so I'll also say thanks to the collaborators on this work, and thank you. And if there are less questions, I guess there's still a couple of minutes. These online talks are the worst.
I have a question.
Sure.
Coming from the world of chess, when a player considers what to play, generally the variance between the best option and worst option is extremely non-interesting, because usually you just don't consider the all the bad moves. And I think that the interesting variance is like between the options that make you unsure. You're not sure whether to take this path or the other path. Both of them are with seemingly close reward. This is why you are thinking about it. And this maybe tells something about your style or about how you do stuff.
Yeah, so I agree. Yeah, there's actually, so when we looked at this importance score, so it's been used before to train agents to decide when to give them advice. And there was actually exactly what you're saying. There was one paper that said you want the highest gap because it's important. There was another paper that says you want the place where there's most ambiguity. Like, I'm not sure whether, right, like you said, there is two good options and I'm not sure which to take, or the way you talked about it, it's like the one I choose tells more about my thinking. So I think that's a great point, because sort of our intuition was, well, if it's the same, then it doesn't matter, but maybe that's not the right way to look at it if that reveals different strategies. And also it might reveal the confidence, right? It's kind of different. You might have a state where you don't know which action to choose between two actions, but you've already experienced a lot in the world and you're just not sure because you think they're as good. And there might be a situation where you're unsure because you didn't train enough there and you don't have enough data. And that seems very different, right? Are you basing these Q values on many observations or not? So yeah, I guess I agree, and it might be very informative to take actually places where you're debating. And I think what we're trying to do now, where we try to compare different agents, is really look at places where either they disagree on which action is better, or they choose different actions, or they even disagree about how good different actions are, because maybe they have different reward functions and things like that. So yeah, it's a great point. I agree.
Sorry.
I think that the key point in my question was that in cases where your choice matters, but the player can't tell, the player doesn't know enough.
Right. So I think here the challenge is that we used the Q values of the agent, and like you said, maybe the agent is not trained well enough. So maybe a better approach that could address what you're saying is either if a person knows or has a sense of something that's important, and the person sees that the agent doesn't know, or if we have, the problem is we might not know the true Q values. I mean, if we have some expert policy aside for the agent, then yeah, maybe we could sort of compare to that. but I think maybe if the person can say, you know, what they care about, and then choose look at how confident the agent is in states where it should be, that might also help.
Thanks.
Thank you.
Okay, I think we're out of time. So if anybody has additional questions, you can reach out to Ofra offline. So everybody is welcome to unmute and take the speaker. Thank you so much.
Thank you.
Thank you very much.
Thank you very much.
Thanks.
Thank you.
Thank you very much.
Thank you.
And we'll see you all
Thank
next
you.
week. Bye-bye.
Bye.